Yes, thank you. Good afternoon to everyone. So today I will present you my work on toward explainable exploratory landscape analysis, extreme feature selection for classifying the function of the black box optimization benchmark. And this is a joint work with Johann Dreo and Carola and Benjamin Doerr. So first, in this talk, I will give you some background on exploratory landscape analysis, if you're not familiar with this. And then I will give you some outline on this work, explain a little bit the design of the several experiments we conducted, and some results on these experiments. So first, let's start with some background on exploratory landscape analysis. We are in a black box optimization context where we have a simulator and we feed this simulator with sample points. And with these sample points, our simulator will compute some quality of these sample points and will output this quality. And our goal is to either minimize or maximize this quality. And the goal of exploratory landscape analysis is to describe the objective function, so the simulator, the black box function, using what we call landscape features. It's often used with machine learning in order to select and configure the right algorithm for the optimization problem to solve. And so I just talk about landscape feature, but let's dive a little bit more deeper in this. So landscape features, we can compute landscape features with three different ways. So we just sample points in a search space, and we compute the fitness values of each of the search points. And then, as I said, you have three ways to compute features. The first way is to use only the sample points. The second way is to use only the fitness values of these sample points. And the third way, of course, is to use a combination of both sample points and their fitnesses. And we have a tool for this, for computing most of the known features. And this is an R package called Flaco, which is developed by Pascal Kerschke. And overall, you have 17 different feature sets and more than 300 features. And in this work, we are mostly interested in what we call cheap features, which means that we do not require extra sample points. We fix the budget for computing the features, and we don't want to add extra points to this budget. And as an example, you have here some features from the meta model feature set from Mersman and colleagues. So basically, here you try to fit a linear model to your data, and you just want to extract some coefficients, for instance. Here you can extract the intercept coefficients, alpha 0, which can be a feature, or you can also compute the adjusted R squared of this linear model, and this can also be a feature. So the goal in this work is to classify almost perfectly the function of the black box optimization benchmark using exploratory landscape analysis. And more precisely, we want to find the couples, number of features, number of search points that help us classify those functions. And basically, we want to recreate this graph here, which is not a real one, but we want to be able to reproduce it, where here each point represents a couple number of search points, number of features that classify almost perfectly the benchmark. And we are really interested in what are the maximum number of points and minimum number of search points we have to sample in the search space to have an almost perfect classification, and also what is the minimum and maximum number of features we have to compute to have this result. And to do this, we have to, for sure, do some feature computation and also to do some feature pre-selection because the combinatorial is too big. If we list all the cheap features in Flaco. They are 46. And so the going through all the combinations with 46 features is a bit too much. So we pre-selected only 10 features. And how do we do that? So here in the middle, you have the 6 cheap feature set in Flaco. And from this 6 cheap feature sets, first we decided to take out the 4 most expressive features. And by expressive, I mean the feature that distinguish best different optimization problems. And to add more diversity in our portfolio of features, we then add the most expressive features from each set. And so here, for instance, you have the black dots inside each feature set that represents the selected features in the end. And to compute these features, we perform 100 independent run of n sample points for each function in the benchmark and for the 5 first instances. And as we want to do classification, we need to create for sure a train and a test data. So to do this, we first focused on only the instance 1 and take the 24 function from the benchmark. And so for example, here you have 3 features and 100 runs for the function 1. So for each feature, you have the distribution of the 100 runs of feature values. So you have this distribution for each features on the same function. And to create the training set, we took 80% of these 100 runs, so 80 runs, to approximate the distribution for each feature and for each function, for sure. And then we approximate this distribution by the median, and the median only. And this median will compose the training set. So we will associate to the feature number 1 on the function 1 its median, its distribution median. And for the test set, we just took the remaining runs to compose the test vector. And to avoid any bias, we repeat this 20 times randomly. So 20 times we randomly select 80 runs, create the distributions, approximate by the median, and so on and so forth. And still, we are doing classification, so we need some classifiers. And we did not want it to take simple classifiers from the literature, because we wanted to know how the feature behaves and what was how the feature behaves. And so simple common classifiers have common drawbacks. For instance, if you take the k nearest neighbors, this is based on distance. So in really low dimension, like in 2D, it's really easy to visualize the contribution of each features. But if in a higher dimension, this is harder to grasp and visualize the contribution of each feature. And some strange thing happens in high dimension with distance. If you take the decision tree, you do not have this problem with distance, but sometimes decision tree can perform feature selection without telling you. And in this work, we do not want this. We want to do our feature selection. And the same inputs might lead to really different trees, which is misleading for us, because if you have really different trees, it's hard to explain what was the contribution of what feature, actually. So we decided to use a voting system as classifier. And this voting system is called majority judgment. And it guarantees that the winner of the vote had received an an absolute majority of the highest grade given by all voters. So how does it work? We have a little example here. So let's take back our 3 features. We have the ID of our 24 functions. And here we have a matrix of grades. So for each feature, we'll give a grade to each function. And this grade is based to the distance of the test point to the median of the training set, to the median of the distribution. So here the 0 means that the distance of the test point to the median of the distribution of feature 1 used in the training set is 0. So they are overlapping. And we do this for every function and every feature. And then to do the voting phase, we extract for each function, we extract for each function the median value of all the distances for all features. And we want to minimize the median on each function. And so the vote, the winner of the vote will be the one with the lowest median distance. And this is it's for us it's better than k nearest neighbor of decision tree, for instance, because here we can see quite clearly the contribution of each features for each function, actually. And so our experiment here is to go through all feature combinations. And so first we will select a combination of features at random. And then we will train our classifier, so our voting system, with this combination of feature, and also test with the remaining runs. And if we obtain an accuracy which is greater or equal to 98% accuracy, we keep this combination. So we have an almost perfect classification of the benchmark. Otherwise, we just loop again and select another combination of feature to redo the processes. And we do that until we find a good combination, or until we exhausted all the combination of features possible. For the cross-validation, we first wanted to cross-validate on classical classifiers, such as KNN and decision trees, because our majority judgment voting system is not really classical for classification, and wanted to see if our results transfer to more classical algorithms. And also we did a cross-validation on other instances, and we did that for 2 different ways. The first way was to train and test on all instances mixed up. So here, instead of creating a distribution for 100 runs for function 1 only, we create a distribution for 500 runs, so 100 runs by instance, and then do the classification. And we did more classically 1 instance out, where we train on 4 instances and test on the remaining 1. So that was all the setups for the experiments. And so let's see some results. First, let's talk about only instance 1. And we can see that few features are needed to reach our threshold on instance 1. So we performed the experiments for 6 different dimensions and 7 different sample sizes. And if I zoom in, so yeah. If I zoom in, you can see that for a lot of settings, for a lot of configuration, dimension, sample size, actually a really few number of features are needed to obtain our 98% accuracy. Most of the settings are below 2 features, and we go up to 6 only. And interestingly, we found that it seemed to be easier with as the dimension increase. As you can see here that in dimension 25 or 30, you can use less sample points than for lower dimension. And what is really interesting too is that even if few features are needed, most of the time the same features are involved. So if you switch the budgets, most of the time the same features will be in the combination kept. So for instance here, if we take this feature here in for the dimension 20, this is the same feature here for these two budgets. And we saw also that smaller set of features perform better than the whole set. So if I take the same example here with one feature, it means that the accuracy obtained here with one feature is better than the accuracy obtained with the whole reduced set of 10 features. Now, if we look at the first cross-validation on instance 1, so if you look at other classifiers, so here in this plot, we have a budget of 250 sample points. We see that for almost all settings, decision tree and KNN reach also our threshold of 98% accuracy. The only two settings that do not reach this threshold is for decision tree and really high dimension. But this corresponds to the fact that only one feature was selected by our method, and decision tree is actually required by to classify with only one feature, and that's why mainly here we have a really bad accuracy. Now, if we cross-validate on 5 instances, if we train and test on 5 instances, we still obtain good results. Here on this plot, you don't have majority judgments, as by definition, it is not really switched to be used on more than one instance. But here, so you just have KNN and decision tree. And you see again that for most settings, we are above our 98% threshold. And when KNN drops below, it still is 97% threshold. It's not that bad. And still here, we don't have the decision tree classification for one feature. And for the leave one instance out, we see that bigger feature sets perform actually better. So here we are in dimension 20, and for each instance. So here we have 4 classifiers. KNN 10 means the whole set of feature. In KNN 2 mean our selected feature, and the same for our decision tree. And we see that most of the time, a bigger set of feature is performing better. And we think this is happening because some features are not invariant to the transformation of the function. And so if you have only a few features, let's say 2, and one of them is not invariant, then of course it will be more difficult if you let one instance out. Whereas if you have 10 features and only 1 or 2 are not invariant, then it's easier to compensate this behavior. And then that's why you might have better accuracy with bigger set of features. So to conclude this presentation, some takeaways. So the number of features to classify the BBOB function are surprisingly low, and tend to decrease with the dimension, which is quite surprising for us, actually. And more than one instances are due in the early one-out cross-validation to have a bigger set of features. And lastly, the invariance of feature to transformation is clearly a decisive success factor to have good accuracy. Thank you. If you have some question, I will be quite happy to answer it.
Thank you, Quentin.